Operating a solar cell. The solar cell operates on a diode structure in which we have a dark recombination current, J naught, and this is amplified by enhancing the voltage. We have then the thermal generation current opposed by a recombination current that increases. And this is the dark diode equation. So when light is added to the system, it generates an additional photocurrent, the short circuit current, and we obtain the full equation of the solar cell as a function of the voltage. The diode equation in dark shows an onset of recombination that becomes exponential, and with the added current, we obtain a region of nearly constant current, and then it goes down when the recombination current sets in. And here there are two fundamental, very important parameters. The short circuit current is the current at 0 voltage, and the open circuit voltage is the voltage at 0 current. We will also discuss the maximum power point. At the open circuit point, there is no current going out, so that the internal currents, thermal generation, photocurrent, and recombination are compensated. If we decrease recombination, then the photovoltaic increases and also the solar cell efficiency. Short circuit current is the current at voltage 0, so that we are extracting the photogenerated carriers. As we increase the light intensity, then the photocurrent is going to increase. So we have seen current and voltage, but we are primarily interested in the energy developed in terms of power, so that some energy per second comes in the form of solar photons, and this has to be converted to electrical power. A current is going out of the cell at a certain voltage, and the electrical power is the product of current and voltage. The power that we obtain in the external load depends on the voltage point of operation, because at each point in the JV curve, we will have the product of current times voltage. It's much larger if we work at this point than if we work at this point, because it's essentially the area of the square, jota times V. So that we want to go to the point where the extracted power is maximum, and this is called the maximum power point. We can find the maximal power point by multiplying at each point the current and the voltage, and then we have a graphic that has a maximum at a certain point, a little bit after the bending point of this diode curve. So we define the maximal power point, and here the current and voltage are not at the maximum. We are at an intermediate voltage, this voltage, and intermediate current, but here the power extracted is maximum. As said before, we can have the maximum power point observing the maximum, and then we have here the voltage of maximum power and the current of maximum power. And then the maximum extracted power is the product of the two. The solar cell efficiency will be the generated power divided by the incoming power of the light source. To deal with this question of the maximum power point, we define a useful number that is the fill factor. The fill factor is the product of the current and voltage at the maximum power point divided by the current and voltage at the maximum point, VOC, and the total photocurrent. So this is the division of these two areas, and it's related to the shape of the JV curve. If we have a good diode equation, then the fill factor is going to be 0.85. If we have a straight line, it is much less. The maximum power point is around here. And then the fill factor is 0.25, as we see in the graphic below. The total power is JV. The fill factor is the product at the maximum power point and the maximum values. And then the power conversion efficiency can be expressed in terms of the fill factor. And it's a product of three things: the photocurrent, the fill factor, and the VOC. So this is the three things you have to optimize in order to increase the power conversion efficiency of the solar cell. Starting from a diode equation with an ideality factor M, we can use the maximization of power and obtain an approximated formula that gives the fill factor only in terms of VOC and the ideality factor M. So the fill factor decreases when the diode ideality factor becomes larger than 1. And here we can see some examples of the factors that affect different photovoltaic technologies. The solar cell is operated by light and voltage. It can be represented by an electrical model in which we have the current source, which represents photogeneration. The diode is the internal recombination current, and two additional elements, a parallel or shunt and series resistances. Series and shunt resistance decrease the solar cell efficiency by affecting the fill factor only, not the short circuit or VOC value. But if the series resistance is very large, then in the end you also affect the photocurrent. Another issue is to apply impedance spectroscopy, and then the equivalent circuit is different because here the diode becomes a resistance, as the circuit will be different at each voltage point. And it will see also the capacitive charging of electrons in the conduction and valence band, and this is represented by the chemical capacitance. In summary, we operate the solar cell with light and voltage. Voltage can be regulated by the external load, and we can move from VOC to intermediate value where there is charge extraction at a certain voltage, and finally to short circuit where voltage is 0. And having obtained the efficiency, we now can make arguments to see the quantity of energy that is converted depending on the source energy. So we can see, for example, that the energy is basically current times voltage. So there will be a correlation with the voltage, and there will be also a correlation with the band gap in terms of the photocurrent that we can take. This we will analyze in a later chapter.